Now let's look at the comparison to GPS velocity. The RT is able to provide much lower noise velocity than GPS. Around trees and other obstructions, the GPS has spikes and drops out. The RT smoothens the GPS signal. The RT also has lower latency than GPS. Speed and velocity are very important quantities for vehicle testing. Car customers assess the vehicle based on acceleration times and braking distances. Both these measurements require accurate, noise-free speed measurements. Most vehicle test tracks do not have trees, but where there are trees, the performance of GPS velocity is reduced. The RT can maintain a high level of accuracy even with some tree cover. In the case of brake distance, low latency is also important, since the delay of 50 milliseconds in your measurement can lead to an extra 1.4 meter braking distance at 100 km/h. The total braking distance is typically 50 meters. With ABS, the distance between a low performance car and a high performance car is about 3 meters, so a 1.4 meter measurement error is very significant. The top graph shows the velocity measurement of an open country road. In open sky, the performance of a GPS is good. Here we see the GPS in an unfiltered state, directly from the raw data. Many GPS products employ filtering to smooth the data, but this can lead to latency in the measurements, though it does improve the output considerably. The output of the RT is smooth. As expected, its long-term value follows the GPS, but it does not contain the short-term noise that the GPS exhibits. Below, the effects of a single tree on the GPS was larger than expected. The tree affects the speed 8 seconds into the test. The test was repeated 3 times, all with similar results. With filtering, this noise would appear much smaller. Notice how, in general, consecutive samples are above then below the actual speed value. This is typical of the raw GPS signal. A simple moving average filter with even number of taps is very good at solving this type of noise problem and works well at smoothing the GPS. In dense cover, we start to see some GPS dropouts. This stretch of road is worse than the picture suggests, and we were surprised that the GPS could provide anything. In summer, when the trees are covered with leaves, there is far less coverage. Under these circumstances, the GPS stops being useful as a measurement tool. No amount of filtering is going to help. Under this bridge, there is no GPS signal. The bridge is too wide for the GPS to be able to track signals on both sides at once. It had 6 lanes of motorway, complete with a hard shoulder. As expected, the GPS signal drops out whilst under the bridge. The RT detects the deceleration to acceleration transition during the time that the GPS is not present. Now let's look at the optical slip sensor comparison. Optical slip sensors have been the standard for slip angle measurement for many years. The RT provides an alternative with many advantages. For example, internal mounting close to the center of gravity, a wide bandwidth, low noise, fast mounting, provides many other measurements besides slip angle. Also, for the comparison, the tests show also include step steer, frequency analysis, and steady state. Continuing to look at the optical slip sensor comparison, the graph to the left shows the path driven for many step steer tests. One test is highlighted in blue. Continuing to look at the optical slip sensor comparison. This test is a step steer where the steering wheel is released at the end of the test. The top graph shows the slip angle at the center of gravity reference point. The middle shows the slip angle at the front wheels and at the rear wheels. The bottom graph shows the lateral acceleration. Two effects can be seen on the vehicle: the step response of the vehicle to the turn and the stability of the vehicle at the end of the test when the steering wheel is free. There tends to be more oscillation when the steering is free. The black represents the RT and the red is the optical slip sensor. Comparing the two results show that the optical sensor has longer latency. The red graph is delayed compared to the black. There is also more oscillation on the optical sensor. This is likely to be a mounting issue with the optical sensor. Since it is hard to mount the optical sensor rigidly on the outside of the car, this is still a disadvantage of the optical sensor. Let's continue to look at the optical slip sensor comparison. In this data set, the vehicle is driven in a circle. The speed is increased until the vehicle skips. This example shows how the optical sensor and the RT measure the same quantity when there is no transient of dynamic effects. The top graph shows the slip angle at the front of the vehicle. The bottom shows the slip angle at the rear. The bottom graph shows the slip angle at the reference point, center of gravity, and shows a lateral acceleration. In this final comparison, we see the response of the car to different frequency sinusoids. To interpret the data, assume that the driver puts the sinusoidal input to the steering wheel at a fixed frequency. The car responds by turning left, right in a sinusoidal manner. The engineers generally use this type of graph to determine the stiffness of the car suspension. A responsive vehicle will have a minimum of the graph above 2 Hz, whereas a poor vehicle will be closer to 1.5 Hz. For accidents avoidance, vehicles with a stiff suspension are easier to drive. They also feel like they have more responsive steering. This type of test is very useful for comparing different vehicles and making objective measurements about which one steers for the best in dynamic conditions.